I just want to do another video now based upon page 10 and optical isomerism. So in the previous video for page 9, we covered geometric isomerism, which is a type of stereoisomerism. The next one that we need to cover is optical isomerism. Now, optical isomerism, and I'll get more into what this is in a moment, but I just want to explain the complexes. Now, we find this type of isomerism in transition metals where they are bonded to 3 bidentate ligands. So if you remember, a bidentate ligand is one that can donate 2 pairs of electrons to the transition metal ion. So therefore, each ligand will form 2 coordinate bonds to that transition metal. So we've got 6 bonds still, which would mean it's octahedral with 90-degree bond angles, but we've actually only got 3 ligands in there because each one forms 2 coordinate bonds. Now, the example that I'm using with this one is iron 2+, and it's bonded to 3 ligands of the ethane 1,2-diamine or 1,2-diaminoethane, the other name for it. Now, when we're looking at optical isomerism in octahedral complexes, you must make sure that you draw them with the wedges and the dashes. So if we draw the first one, I'll draw it on the left-hand side of the paper. So we've got the iron, then we're going to have the bond there, and the bond there, and then we show the 2 wedges, there, there, coming towards us, and then the 2 dashes disappearing behind. Now, in the ligands ethane 1,2-diamine, it's the nitrogens that possess the lone pairs of electrons. So we've got an N at each end. And then rather than draw the CH2 and the CH2 which link these, we can do it skeletally. Also, make sure you don't forget the two hydrogens. So just draw those at the side, but make sure they're not at the end of the stick. And that has a 2+ charge overall. You're not expected to learn this complex. It's the application of the isomerism, whereby a transition metal ion is bonded to 3 bidentate ligands. Now that's one arrangement at the moment. That's all that we've done. Now it's got a molymod kit here, whereby we've got the yellow transition metal ion in the center, the 3 ligands, which have been just simplistically they're shown as the black balls here, and then we've got 2 coordinate bonds coming off each one. Now that's that one. What we've also got, and this is a Cath special, we've got glitter on each of these to represent the bonds, which will be very useful in a moment. Now that we've got that, if we're to draw the mirror image of that, so imagine that we've got a mirror down the center here. You don't have to draw this, but we've got the mirror there, and then we draw the mirror image of it. So we do our bonds there, our 2 wedges here, the dashes going back there, ends at the end, and then we need to join them up. Now we can see that this bond here is closest to the mirror, so that one is going to join these 2, so it's closest to the mirror. Then these 2 bond together, and these 2 bond together. Put your H's in, And then we can draw that. And I forgot the charge on the previous one. Now they don't look really any different aside from the fact that I can't reproduce the scale going from one diagram to another. But if we were to have that one, and it was a mirror image of that, it would look like that. So you can see that with this, we've got the bonds which are in mirror images of one another. The gold one at the top there, the red one behind it, the red one at the bottom, which will be closest to the mirror there, and so on. But to check if they're the same, and because we're dealing with stereoisomerism, the true test is, are they superimposable? If they are superimposable, that means that it's the same structure. They're not really isomers. Whereas if they're non-superimposable, if I put one on top of the other and they don't match exactly, then they're isomers, they're optical isomers. And that's what we have. They do not match when I try and put one on top of the other. So the angles of the bonds are moving in different directions. And it's because essentially, if that's one isomer, the next one, we've bonded those ones together. Now structurally, they look exactly the same, but in three-dimensional space, they don't match up, which means that they're isomers. Now, one way of being able to distinguish between these is if we've got separate solutions of these two isomers and we rotate something called plane polarized light. That's light that has gone through a filter. You don't need to know you don't need to know anything about it other than the name, but it's light that's gone through a filter. And what would happen is this isomer would rotate the plane polarized light in one direction, say for instance clockwise. This isomer would rotate plane polarized light anti-clockwise. So for instance, if this one rotated it 30 degrees clockwise, this one would rotate it 30 degrees anti-clockwise. So they rotate plane polarized light in opposite directions. Now, another term that you may well come across is something called a racemic mix. Now, a racemic mix, or it can be called a racemate, is when we've got an equal ratio of both isomers. So an equal ratio of both optical isomers, and another word for a pair of optical isomers is enantiomers. So if we've got a solution where we've got an equal ratio of both optical isomers or both enantiomers, that means we've got a racemic mix or a racemate. Now the effect upon that, so the effect of a racemic mix on the rotation of plane polarized light is that rotation is cancelled out. So one rotates a certain number of degrees clockwise, the other one rotates it an equal number of degrees anti-clockwise, so the rotation is cancelled out. This is a concept that we'll come on to again in a lot more detail in organic chemistry when we're dealing with the chemistry of carbonyl compounds, but that's definitely a second year topic. So this should be enough to get you through this part of the syllabus in transition metals for the moment. So I hope that explains things a bit better than just a couple of diagrams on the VLE. Thanks a lot.